Okay, we are recording, so I'm going to introduce our speaker today. We are glad to have Runzhe Wu, that is a third-year PhD student at Cornell University in computer science, working under the supervision of Wen Sun. He's doing some great work in reinforcement learning, focusing on developing algorithms grounded in theory and with practical application. Is developing right now efficient algorithms inspired by generative models such as diffusion models to improve the performance in reinforcement learning and imitation learning tasks. And previously he did his bachelor in Shanghai, Yantao University. That's it. So we are very happy to have you today. The stage is yours. Thank you.
Yeah, thank you. Thank you, Luca, for the introduction. Yeah, I'm Runzhe from Cornell University. Today I'm going to talk about this paper, Computationally Efficient Reinforced Learning under Linear Bellman Completeness for Deterministic Dynamics. So this is a joint work with many amazing collaborators, Yush, Akshay, and Wen-san. Yeah, so we have seen a lot of success in reinforced learning with rich function approximation. For example, reinforced learning has been applied to do dexterous manipulation, to play video games like Minecraft, and also even be used to fine-tune large language models. So the theoretical question behind this success is, can we design provably efficient reinforced learning algorithm under rich function approximation? And this is also the main question today. But for today, I'm gonna mainly focus on the specific class of function, that is linear function. And more specific, I'm gonna focus on the specific problem of linear Bellman completeness. And it's kind of surprising that even for linear function, there are so many things we still don't know in theory. And this is the outline of the talk today. It's gonna be 3 parts. In the first part, I will talk about the background of linear Bellman completeness. In the second part, I will talk about the algorithm. And finally, I will talk about an important issue of the norm. Okay. So, okay, first, let's dive into the background. And before talking about the specific setting of linear Bellman completeness, I think it's better to get a big picture of our current progress on efficient reinforced learning. So let's look at the following. So here I'm going to show many classes on DP, and I will use screen check to denote that we know computationally and statistically efficient algorithm. And I'm going to use the red question mark to denote we only know sample efficient algorithm for the MDP. And we'll start from the most simple one, tabular MDP. We know we have computationally efficient algorithm, and it's also minimax optimal kind of thing. And a little bit beyond that, we have linear MDP, and we also know how to solve it. And a little bit from the control side, we also know how to solve linear quadratic regulator, or LQR. And then here comes the main focus today, that is the linear Bellman completeness. And I mean, as you can see here, linear Bellman completeness captures both LQR and the linear MDP, and of course tabular MDP. But we only know sample efficient algorithm for linear Bellman completeness. It's actually still open whether computationally efficient algorithm exists. And if we go beyond that, we will have low Bellman rank and low witness rank, and we don't know computationally efficient algorithm for that either. And we can go further. We have low bilinear rank and the Bellman eluder dimension. And there are actually more. I just show a few here. Yeah, so today we're gonna focus mainly on linear Bellman completeness, and the open problem, which remain open today, is that does computationally efficient algorithm exist under linear Bellman complete? And this talk, I mean, our work is trying to solve this open problem, but we only solve it partially. So our answer is yes, computationally efficient algorithm exists when the transition is deterministic, right? In other words, we propose a computationally efficient algorithm, but we require the transition to be deterministic. And yeah, so I was trying to emphasize the assumption made in this paper. So we only assume deterministic transition, which means we allow the following: the adversarial initial states, random rewards, and the large action space. Right. So this actually separates ours from separate our setting, linear Bellman complete, from the setting known as linear Q star, where deterministic transition alone is not enough. Right there, you usually need more. You usually need deterministic initial states, rewards, and you usually need some gap assumption on the value function. And yeah, just for simplicity today, I'm gonna assume norm rewards, because reward learning in our algorithm is actually quite standard. Yeah, so here is some notation. So I'm gonna use episodic finite horizon MDP today, which means I'm gonna start from state S1, and then we take action A1, we receive reward R1, and then we transit to state S2, and then we take action A2 and keep doing this, so on and so forth until we reach S capital H. Then we take action AH, then we are down there. And also the notation for value function, I will denote the state action value function by Q pi H, which means the state action value function of pi at step H. Right? It's just defined usually. And also denote the state value function by V pi H. And I will use V star H to denote the state value function of the optimal policy. And the goal is to minimize regrets. And the regret is defined as usual. It's the expectation of the summation over capital T rounds, right? The summation of the performance gap. And yeah, now let's formally define linear Bellman completeness. So we say that MDP is Bellman complete.
So just a clarification, when you say you allow adversarial initial states, do you just mean S1, or do you also mean the initial states at the restart of every episode? In the slide before?
Sorry, could you say again?
When you say you allow adversarial initial states, is it
Yeah.
just the very first one, or also the initial ones on the next episodes?
Yeah, just the very first one, right? Like S1 here, like yeah, when we start the MDP, we get the initial state. I mean, that one could be adversarial chosen.
But I think
Okay.
he's asking whether that's the case only for the first episode, or I think it's for all episodes, right?
Yeah, for all the capital T episodes.
Yeah.
Oh yeah. Okay. Sorry, my bad.
Yeah.
Oh yeah.
Sorry. Yeah. Yeah. Like yeah. Okay. Good. Yeah. So we say that MDP is Bellman complete with respect to a function class capital F, where F is you can think about the function class F as a function of mapping from state action to real numbers. Right? You can think about it as some estimators of state action value function. We say this Bellman complete if for any function F in the function class, the red part is still in the function class. So what is the red part? The red part, if you are familiar with it, it's basically the Bellman operator. Right? The red part is a mapping from state action pair to the reward function plus the transition part, which is S sample S prime and compute the max over A prime, then F of S prime in A prime. This is essentially the Bellman operator. And in other words, it's saying, okay, if I apply the Bellman operator to any function in the function class F, then I get back a function in that function class as well. And the linear Bellman complete is essentially saying when the function class F is linear. Right? By linear, I mean all the function in the class can be written as the inner product between some norm feature phi times some parameter theta, where we usually assume the feature phi is known. Okay. yeah, so that's pretty much the background. And I'm now try to talk about the algorithm and the main trick of the algorithm. And before introducing our algorithm, I think it would be better to first talk about a classic algorithm called RSVI. This algorithm is designed mainly for linear MDP, but the reason I want to introduce it here is that our algorithm is mainly motivated by this algorithm. Okay, so the RSVI algorithm is kind of iterative algorithm. It has two for loop. The outer loop is just just goes through all the iteration, and the inner loop is going back, like enumerating from capital H and going backwards all the way to 1. And at each step, just like any other LSVI kind of algorithm, it first do the linear regression on the parameter. So what they did here is they try to fit a linear function so that it can learn the state action value function of our estimates. And then the key of this algorithm is that they gonna sample a noise Xi from some Gaussian distribution, where the covariance matrix is just the inverse of the datagram matrix. And then they compute the Q function by they denote the Q function as the inner product between theta plus Xi times phi, which is the feature, and the clipped function at H. Right? And then they compute the V function as usual. Okay, and finally they let the current policy pi t be the greedy policy with respect to QH, right? Just by taking argmax of QH, and then they collect new data by pi t. So this algorithm is actually quite standard. How it works, the key idea here is that if we set Xi, the noise here, to be appropriately large, then we can argue that Xi can cancel out the estimation error, which I denoted by theta h by theta star h. I denote the theta star as the base optimal of the regression problem in the first line there. If we set the Xi appropriately, then we can cancel out the estimation error to achieve optimism with constant probability. And optimism is really what we need to argue our algorithm has no regrets or something like that. Okay. And as I mentioned earlier, RSVI kind of algorithm, this algorithm is designed mainly for linear MDP. So a natural question is, can I apply this to linear Bellman completeness? So as you can see from this algorithm, that it didn't really leverage any explicit structure of linear MDP, right? So for linear MDP, you have factorized transition, you have factorized rewards. But seems that this algorithm doesn't explicitly using them. And we know linear Bellman complete is a larger case that capture linear MDP. So can we just extend this algorithm to linear Bellman completeness? And I'm putting the definition of linear Bellman complete on the top right for your reference. It's basically saying for any linear function, if we apply the Bellman operator, I get a linear function back. And actually, it turns out that this is not really possible. And the reason why is that the regression will kind of fail. Why will it fail? Because you can see the regression here is actually a linear regression. That means they try to find a linear function to to fit something. That means the base optimal here must be linear. However, it's unclear if the base optimal here it could be linear, because if you look at the following two parts, we only know that the green part is linear, right? Because it's just defined as a linear function. It's an inner product between our estimator and the feature. This is linear. However, when we apply the inner product, this is linear, but when we do the clipping at H, the Q function is probably no longer linear, right? So this is the issue, because the base optimal at the regression is exactly the function you will get by applying the Bellman operator to Q function. if Q function is not linear, then there's no guarantee that the base optima is linear. The linear Bellman completeness only says if I apply the Bellman operator to a linear function, then I get a linear function back. But when it's nonlinear, we don't know what will happen. So this is the issue. Right. So in other words, I'm saying the base optima is nonlinear, so the regression will fail. So a natural idea would be, okay, seems that all the problems here are because of the clipping. If we don't clip, seems that everything is good. Right? We have linear function for Q function, and then therefore the base optima will also be linear. Seems that everything is good. Okay, so I remove the clipping, and yeah, let's think about this unclipped version of the algorithm. Yeah, so I mean, clipping is actually quite important. Yeah, so now I will show why clipping is kind of necessary, because if we don't do clipping, there will be some problem of the norm. Okay, so for now, let's fix an arbitrary h, and I'm assuming that our estimator theta h at that round is the norm of it is L, where L is just some parameter. And as I mentioned earlier, if you still remember, for this algorithm to succeed, we have to set the noise C to be roughly, I mean, at least as large as the estimation error, so that we can cancel out the estimation error to achieve optimism. That means the norm of the noise also has to be roughly the same as the norm of the estimation error. And I'm gonna denote the regression error by the norm of the theta times some epsilon. You can just think about epsilon as some standard quantity you will get from regression. Yeah, so if I assume the norm of theta is bounded by L, then when I inject the noise into a theta h, right, then the whole thing will have norm 1 plus epsilon L, where the epsilon L just comes from the C. Right. That means the Q function will kind of also have the size of the Q function will be roughly 1 plus epsilon L, because Q is just defined by the inner product of this estimator and the feature. And if Q function is bounded by that, then we recall that the base optimal is just by applying the Bellman operator to the Q function. Right. That means the base optimal of the regression problem probably also going to have norm bounded by that. That means my estimator at the next round, h minus 1, will probably also have norm as large as 1 plus epsilon times L. Right. And I'm going to do the same thing. In the next round, I'm also going to add noise. That means the norm is going to increase by another 1 plus epsilon. Right. And the Q function will also increase by another 1 plus epsilon. And as this algorithm proceed, we will add many noise. That means the norm of all the parameters is actually going exponentially fast. Right? As you can see here, the power is actually going linearly. So the conclusion here is that if we don't do clipping, the noise will actually make our parameter, the norm of our parameter, grow exponentially fast. And this is actually kind of terrible. Yeah, I want to dive more deep into why this is terrible. So let's recall how we usually do analysis for LSVI kind of algorithm, including RLSVI. So our arguments will start from regression. We will first argue that, okay, if I do regression appropriately, the regression error is small. Right? You will get something like this. And given regression error is small, we were going to argue that, okay, Bellman residual is also small. And if Bellman residual is small, we finally can argue that the performance gap is also small. Right? This is how we argue for OSVI kind of algorithm. Now just think about it. If the parameter theta has exponentially large the norm, then what's going to happen? So first, this term is gonna explode as well, because you can see that this term explicitly depends on the size of theta. So this term is also gonna be exponentially large. And if this is exponentially large, then it's super bad, because everything else is gonna explode exponentially. And since that this is very bad and unavoidable, because once we have our parameter exponentially large, then it kind of ruined our proof. But let's think about this problem a bit deeper. Let's think about it more carefully. I think this is actually really unavoidable in general, but this is also where our algorithm is gonna deviate from this RSVI kind of algorithm. And actually, we've realized that if we have deterministic transition, then we can kind of bypass this issue in some sense. So to summarize, actually, we find a solution. That is, when the transition is deterministic, we can possibly just add a noise in the null space of data to avoid this issue. So what I mean is, I'm gonna add a noise only in the null space of the data, so that the explodes only happen in the null space. It will not happen in the span of my data. Right? So if it's not only happen in the null space, then in the second step and the third step, this blow up will not matter. Okay, so yeah, this is the high level idea of our algorithm, also what I'm gonna do. And before talking about more detail of the algorithm, let's also focus on the key observation here. That is, let's focus on the regression of RSVI. Okay, so this is the regression of RSVI. Let's think about it. So let's say the transition is deterministic. Then what does it imply for this regression? So if transition is deterministic, then the first thing we probably know is that VH plus 1 of S prime is deterministic as well. Why? Because if the transition is deterministic, then S prime is pretty much deterministic, even SA, right? So that means what we're regressing is actually deterministic. And this is actually very good, because this is saying our risk minimizer actually zeros the empirical risk, right? Because this regression problem now doesn't really have much randomness in the targets. So the base optimal should zeros the risk, and therefore all the empirical risk minimizer we can compute should also make this quantity zero. And what does it mean to have this quantity zero? It means so now I draw the span of my data as the blue part and the null space as the orange part. So this is saying if this empirical risk is zero, that means my estimator theta h is accurate to the base optimal theta star h in the span part. That means the estimation error is gonna be perpendicular to the span and only belongs to the null space of the data. If we're gonna make it more mathematically, let's denote pH as the orthogonal projection matrix onto the span. Then this is basically saying, if I project the difference onto the span, then we got zero. If I project it onto the null space, then we get the error itself back. Yeah, so how do we leverage that observation? Let's go back to the RSVI algorithm. So the key of RSVI algorithm is that they sample noise so that you can cancel out the estimation error to achieve optimism. And if you look at it more specifically, you actually sample a noise from the whole space, from the full space. And as we argued that under deterministic transition, our estimate is actually accurate under the span. So there's really no need to explore in the span. We can just ignore the span parts and only explore the null space parts. In other words, if I do the following, then the algorithm should still work. That is, I'm gonna project the noise onto the null space. Right? I just multiply the noise by 1 minus I minus p, which is the projection onto the null space. Then I get the projected noise, xi tilde. Then I only use this as my noise in the computation of the Q function. Okay. And yeah, as we argued earlier, this should work. And we can also simplify the whole thing a little bit, because we first sample xi, and then we sample xi tilde. We can just simplify them into a single line. This is below the xi
Quick
tilde.
question here. So when you say null space versus span space, it's not that binary in the actual situation, right? Because you can have, do you like, for example, set a threshold for the eigenvalue or something like that?
Yeah, so actually, so we will argue that under deterministic transition,
Oh,
when
I
I
see.
did,
Then it's like very binary, like either you've explored it or you have not.
so in algorithm, we really treat the span, the null space, two separate things.
I see.
Yeah, and I will show more in some analysis later. Okay. Yeah, so we can simplify the two lines into one line to just want to make our algorithm easier. Yeah, so this is what we got. And yeah, this is pretty much our algorithm. We basically just change one line from our SVI. We just change how they do noise. But here is a caveat. The algorithm looks simple, but it's actually not that simple. One issue here is that setting the variance here is actually quite challenging, and I will talk about it in the next section. I'm gonna, for now, I'm gonna assume I know how to set sigma, but just keep in mind that setting the sigma here is not very easy. Okay, yeah, so for now, just assume, okay, this is pretty much our algorithm. I can set the noise appropriately. Okay, now I want to dive into some high-level intuition of why this algorithm can work. So the proof of this algorithm relies on this, what we call the span argument. So for now, I'm gonna fix around t, right? So t is basically the index of different rounds. For the span argument, I'm gonna consider two cases. The first case on the left is called the all-in span case. For this case, it means that for all h, the feature phi of sh and ah is in the span. Okay, so and the sh and ah is the trajectory I got by rolling out pi t. Right, this means all my trajectory is in the span. And on the right, it's the second part, the second case. This is saying this is called sum in null space. It means there exists some step h such that the feature is not in the span. Right, that means that feature could have some non-space component there. And the proof is actually two parts. I proved the both case separately. Yeah, let's first think about the first part. I copy our algorithm here. I didn't change anything. I just copied it for reference. And under the first case, there is actually a very interesting observation. That is the following. Let's think about how we compute QH, right? So QH of SH and AH, by definition, is equal to the inner product between theta plus xi tilde times the feature phi. This is by definition. And under our assumption, the phi, the feature, is in the span. However, the noise, xi tilde, as we define this in the null space only. So their inner product is going to be 0. So we can just remove xi tilde. And we arrived at the middle term. And then if I remember earlier, I mentioned that the empirical risk is going to be 0, which means our estimator and the base optimal is going to be accurate in the span, right? That means we can also replace my estimator theta h by theta star h. Okay, this introduced no difference. And what is the last term here? It's actually what we compute as the q pi th, because pi t is actually taking the argmax of the q function. So this is just q pi t. So what this equality tells us is that if case 1 happened, then for all the h, my estimate qh is exactly equal to q pi th. I mean, on the trajectory that's rolled out by my policy pi t. And consequently, the value function will also be equal. I just moved the conclusion here. We have the value function being equal. And also, one key argument from RSBI is that I can argue that the optimism happened with constant probability. I'm gonna ignore this part, but I mean, I'm just assume that this inequality is true. I'm gonna assume optimism holds.
Regarding that, so
yeah.
So this optimism, so there are two. So there are two different versions of optimistic statement. One is that your estimated value is higher than the true optimal value at the initial state, which is what you show here. The stronger one is that it's greater than the optimal value at every single state, which is a sufficient or stronger condition. Which one do you satisfy here? Both or only the weak one?
Yeah, just as I mentioned, I only need the weaker one. I only need the value function at the first step to be larger.
But how does that? But usually that requires a fixed initial state distribution, right? How does that play with the adversarial?
Yeah, so we can imagine this as, so first I generate a bunch of initial states, but I don't know what they are. They just some people generate them. Then I'm gonna argue on this sequence.
Oh, but I guess there's a little bit of subtlety here, is that then your adversarial initial states are oblivious adversary, right? They're not a dynamic adversary that can change the next episode initial state according to what you have done in the past.
Yeah, I think, I think you're right. I think we should kind of consider this to be, it's fixed at the very beginning.
Yeah.
I don't know what they are.
It's oblivious. Oblivious. It's like the adversaries are set at the beginning of the game before you take any action. But anyway, yeah, I see. Okay.
Yeah. Thanks for bringing this point. So we only need optimism in the first step. So this is what I wrote here in the red. Okay, so these two rules are enough. So given these two rules, we can show the following. So the per round regrets is just V star minus V pi t. Then I'm gonna use optimism. This is saying V star could be bounded by our estimate V1. And then I use the blue part, blue equality. I will replace V pi t just by V1, our estimate. Right, and it happens that this is just 0. So what this means is, okay, when the case 1 happened, that means all my trajectory is in the span. Then we basically have no regret at that round. I mean, 0 regret. Okay, so this is the first part. We show that on the first part, it works very well. The regret is just 0. And what about the first? What about the second part? There could be some feature that is not in the span. But however, if that happened, we can argue that in the next round, t plus 1, the dimension of my span will increase by 1, right? Because we are gonna add that point into our span, and that point is not in our span. Then after we adding that into our span, it's gonna increase. But we also know that for all h, the dimension of the span is upper bounded by d, where d is the dimension of my linear function. That means the whole thing can happen at most d times capital H times, right? Because there are capital H many spans, and each of them has dimension d. So the whole thing will not happen for more than d times capital H times. Yeah, and this is pretty much for the second case, and it's actually very simple. So in summary, we have shown that for the first case where all the features are in the span, we have no regret. And as a kind of reminder that this is kind of intuitive, we actually need to incur some polynomial regrets in case 1 because we are not going to argue the optimism. But for now, just as an intuitive explanation, we can just think about it as 0. And also in the second part, we showed that the regret is bounded by dh times h because case 2 only happen for at most d times h times, and each time we just pay capital H as a regret. That means if the reward is known, if you remember, I assume norm reward at the very beginning. If no reward is known, we have the regret bounded by d times h squared. And it's actually independent of t. And if we want to add the reward learning back, it's actually quite standard. I'm not going to too much detail about it now because it's just standard regret learning. So if you add a regret learning into our algorithm, reward learning into our algorithm, the regrets will be something like this. So as you can see, now we have a dependence on capital T. And the T only arises from the reward learning because we use the elliptical potential lemma. Yeah, so that's pretty much the high-level main theoretical result of our algorithm. And here is a reminder that we are not done yet. We just show that, okay, if I know how to set sigma, then everything will go like that. But as I mentioned earlier, setting sigma is actually not quite easy. It's not straightforward. And this is what I'm gonna talk about next. Yeah, so now I'm gonna go into the third part, the norm issue. And before that, is there any question? Okay, so what do I mean by the norm issue? Let's go back to our algorithm. I just copied the algorithm here. If you remember, we have to set the noise C tilde large enough, at least as large as the estimation error, so that it can cancel out the error. That means the Xi, roughly the Xi, the value of Xi has to be larger than the estimation error. Since Xi is sampled from the Gaussian noise here, right? The Gaussian noise with covariance matrix sigma squared times I minus P. That means the sigma H has to be roughly at least as large as the estimation error. But the question is, how large can this be? How large can the estimation error be? We have to know how large it is so that we can set sigma H. And this is actually not very straightforward because we can think about the following. I'm going to do a thought experiment for now. I'm going to assume, let's say I fix H. I'm going to assume the norm of theta H plus 1 and the norm of the base optimal, theta star H plus 1. I'm assuming both of them are bounded by capital L, where L is some parameter. And since the noise has to be roughly the same or larger than the estimation error, by triangle inequality, we can show that the noise should have norm bounded by 2L. Okay, and then I'm going to inject the noise into our estimator, theta H plus 1, right? So the whole thing by triangle inequality again is going to bounded by 3L. And then here comes the issue. That is, okay, I know that theta H plus 1 plus my noise Xi, I know this vector has bounded norm, but I don't really know if the base optimal at the next round, at the next step, H, I don't know if the norm of that is bounded, right? So let's recall that theta star H, the base optimal, is exactly what you will obtain by applying the Bellman operator to the theta H plus 1 plus the Xi tilde. Right? This is just by applying Bellman operator. But however, the linear Bellman completeness says nothing about how large the norm can grow. Right? It's possible that the norm of theta plus c tilde is bounded by 3L, but after applying the Bellman operator, the norm can just grow arbitrarily large. There is just no control on this. So there's no way we can know how large the size of theta star is, and therefore there's no way we can know how large the estimation error could be. And therefore we really don't know how to set sigma, because we need to set sigma to be larger than that. So in summary, the issue is that linear Bellman completeness alone actually allows arbitrarily large norm explosion. And as a consequence, for this algorithm, we don't really know how to set sigma h. We don't know how large the estimation error could be. And this issue is actually kind of fundamental and general. It's not just for this kind of algorithm. Basically, whenever you want to do the backwards regression thing for linear Bellman completeness, you will face this norm explosion issue. You just cannot control the norm explosion between different steps. And let's see how prior works try to solve this problem. I copied the linear Bellman completeness definition on the top. As a reminder, it's saying for any function f that could be written as the inner product of phi and theta, there is another function f tilde equals to theta times another vector theta tilde, such that f tilde is the Bellman operator applying to S. Okay. And let's see how prior work solved the norm explosion issue. And so the first assumption that the prior work has been making is that they're going to assume that the norm of the vector theta tilde is bounded by some prefixed parameter r. Right? So this is saying, okay, whenever I apply the Bellman operator to my estimator, then the resulting vector has bounded norm, like by r. And I would say this looks not so natural, because why do we believe there is a bounded norm, right? Why do we believe there is a bounded constant r here? And the prior work also tried to do an alternate assumption, that is, they just assumed Bellman operator is non-expansive, in the sense that the norm of theta tilde is bounded by the norm of theta. Right? Just after applying the Bellman operator, the norm doesn't increase. And this is actually very strong, because this is not even true in tabular MDP. And we don't really want to make those strong assumptions. And fortunately, we found something interesting. So here is our observation. Let's think about this inequality. If I want to compute max over SA, phi of SA times theta tilde, then by definition, theta tilde is exactly what we get by applying Bellman operator to theta. So we can write the first term by the following in the middle. It's basically equal to reward plus the transition S prime and the max A prime, and then the linear function of theta. And then since we assume reward is bounded by 1, just for regularity, the whole thing is bounded by 1, plus taking max over SA of the inner product. Right? I can just merge all the max in the second term by a max over SNA as the inner product. And then now let's define the left-hand side as a new norm, which we call the L infinite functional norm. So the left-hand side is the L infinite functional norm of theta tilde. And the right-hand side is 1 plus the L infinite functional norm of theta. And what this inequality tells us is that the linear Bellman completeness actually controls L infinite functional norm. Right? In other words, it doesn't control L2 norm, it doesn't control other norms probably, but it does control L infinite functional norm. And this is important because we really need to control the norm in some sense so that we know how large it is. And also want to emphasize that this is not an assumption. This is just a conclusion. We're not making an assumption. This is just what we can get from the definition itself. Yeah, so let's do a second visit to the norm. So previously we showed that when we try to argue on the L2 norm, we actually stuck in the middle because we don't know how the norm can increase. But now let's just replace all the norm by the L infinite functional norm. And let's do that again. So let's start over. I'm going to assume that the L infinite functional norm of theta and the theta star, both of them are bounded by some parameter L. Then I also going to add the noise roughly at the same size as the estimation error. So this is going to be 2L. And after injecting the noise into theta, I got 3L. And this is the key step here, because previously we were stuck here because we don't know how large L2 norm can increase. But now we know it because we're using L infinite functional norm. We can show that, just using the inequality in the previous slide, we can show that the norm of the base optimal at the next layer only increased by 1. So that is bounded by 3L plus 1. And this is great because, okay, at least we control the base optimal. And then the next question is, okay, we control the base optimal. We also need to control the norm of my estimate, that is theta h. And how to do it? It's actually quite simple. We just enforce the regression problem. So you have the norm bounded by 3L plus 1. So basically, I turn the regression problem into a constrained one. And since we control both norms, we can show that, okay, by triangle inequality again, the whole thing, the estimation error is bounded by 6L plus 2. And yeah, now we can safely set sigma to be larger than 6L plus 2. Yeah, now we are really all set about the algorithm. And I can also, yeah.
But
please.
then is that still computationally efficient?
Yeah, you mean the regression, right? Yeah,
Yes.
I'm gonna talk about this soon. Yeah, basically in the next part. Yeah, so if I assume that the algorithm, I assume the regression is solvable, then this is pretty much what we need to do for this algorithm. Right? Then we can keep doing this argument for h-1 and h-2, keep on doing this, then we know how to say all the sigma, then we're pretty much there.
And how does error accumulate over horizons?
So sigma will grow exponentially fast. As you can see here, it goes from L to 6L, so it will go exponentially fast. But due to the span argument, this thing is not gonna appear in my sample complexity. It's only used
so
to
this
achieve.
is also where deterministic is playing a huge role.
Yeah. So if this thing show up in the sample complexity, then we are doing.
Does seem like exponentiation.
Yeah, I think that's the key usage of deterministic transition. We just make sure that the null space doesn't really affect what we have now. Okay, so yeah. So what's left is this constraint square loss regression problem. I just copied the regression problem here. This is what we need to solve. And I want to make it more general. In general, we actually need to solve the following. Right, which is linear regression, square loss, subject to some constraint that looks like this, right, where the W could be exponentially large. This is what we need to solve. And so this is pretty much an optimization problem. And fortunately, we find that this is solvable. We find a prior work that used random walks that can solve this problem. And their computational, their running time only depends in log of W. And actually, the log of the size of the constraint space. So if W is exponential here, then log of W should be acceptable. But there's no free lunch. That algorithm needs something called the separation oracle, which could be realized by a linear optimization oracle in this case. Yeah, so
And I'll also guess it's not just exponential over W itself, right? It's probably like W over like the accuracy you aim to achieve.
Yeah, right.
Yeah, then the log of that.
Yeah, true. Yeah, we that also involves some precision and also some lower order thing there. Yeah, okay. Yeah, so that means, okay, if I have this linear optimization oracle, we can apply their algorithm and solve this problem. Yeah, and yeah, this is pretty much all about the algorithm. Like we go from the span argument to the issue of the norm, and finally, we need to solve this square loss regression, and we can apply the random walk here to solve the problem. And yeah, so this is pretty much all I want to talk about today. And some takeaways. So we just propose an efficient reinforcement learning algorithm under deterministic transition for linear Bellman completeness. And there are two key ideas. The first is the span versus null space argument. We kind of show that, okay, under deterministic transition, we can separate the span and null space and argue for them separately. And the second thing is for linear Bellman completeness, we probably should use L infinite functional norm instead of the L2 norm because linear Bellman completeness doesn't really control L2 norm. And there might be some other future works. So the first might be, can we extend this span versus null space technique to broader settings? And the second is, since we consider totally deterministic transition in this work, it's natural to think about if it works under using some other techniques. If it work for transition that has low variance, and ultimately, can we hopefully solve the linear Bellman completeness problem? Maybe inspired by this work, and maybe inspired by the work presented by Noah in the previous seminar, and hopefully can we finally solve it. And yeah, so that's the end, and thank you for attending. I'm happy to take questions.
Yeah, I guess I also was just thinking about other. Let me just you can speak up if you want to ask the question directly. There's a question in chat whether G-optimal design in this paper is computationally efficient for infinite feature space. What do you mean by infinite feature space? Do you mean like a RKHS like setting?
Yeah, I think for general infinite feature space, I mean you typically can have some infinitely large feature space. Yeah, I think maybe they're asking for in general how to solve it. I guess this is also an optimization problem. So maybe you'll wonder where is this G or D optimal thing come from, because I didn't mention this in my talk. The thing is, when we move from the L2 norm to what we call the L infinite functional norm, we can no longer regularize the datagram matrix by identity matrix, because identity matrix correspond to L2 norm. So we kind of need some D-optimal design there in replace of the regularization. So this is what we talk about in the paper. And yeah, so I would say this is pretty much a optimization problem. Yeah, so you might achieve this. Maybe you have some Oracle efficient algorithm for it. Oh, yeah, thanks.
Yeah, I also have a question regarding future direction. I guess I'm less I'm less optimistic about low variance because of all these exponentiation of sigma and other things. Like if you are even slightly like stochastic, I think that easily breaks down. Have you thought about? But I've thought about a few additional mild assumptions that some maybe not that mild. So one thing is a few things. One, for example, a relaxation of optimism is to say, oh, for example, suppose I know the optimal return, or maybe I have a sort of a performance bar that I would like to meet, and I know it's feasible. Is that something that will help, right? So maybe you can just repeatedly sample and until you find a parameter that meets that bar, but also has small norm. But then you would only need to argue that that happens, computationally in an efficient manner, that you don't need to sample many times. That's one.
I say you're saying if I whenever I sample, I can be optimistic with some probability, then I just keep doing this. Keep
No,
sampling.
I'm just saying, like, for example, I know the optimal value of this game is like.
Oh, okay.
So then I
I
know
see.
that as long as my estimated value at the initial state predicts something higher than 100, I know I'm good. Like, I don't need it to be like really the highest. So then I can repeatedly sample until the prediction at the initial state is above 100 and the parameters are small.
I see. Yeah,
Something
yeah.
like that, right?
Well, you can just binary search this, right? So there's not really a useful.
No. Like, wait, what do you mean by?
Like if you have a
Assuming-
max value, you can just like do epsilon grid and run all of them in parallel, and one of them will like do something interesting.
No, but if you're in a regret setting, I think.
Yeah, not in regret.
In your online exploration, you can't parallel execute all of these, right?
Yeah, not in regret setting. More.
No,
in the
even like as long as you're in the online setting, it's not easy to do that. It's a non-trivial model selection problem, because like different guess of the initial value would recommend different actions, and you can't take all of them.
Oh, like you can just pay extra 1 by epsilon factor and run all of them in parallel. And
I think for sample complexity, maybe.
Yeah, sample complexity will just get worse.
For sample complexity, maybe.
It's interesting.
So which means that likely it won't work.
Yeah, it's interesting how to do it without this blow up, but I think you can do something.
The other direction I was thinking is that if you remember, like when you mentioned how errors blow up in one of the slides, you said like, oh, it actually doesn't blow up in tabular. And I think maybe there might be a generalization there. Is if you consider, for example, these like a simplex feature setting, like for example, all the fees are non-negative, or even they sum up to 1, and like even all the thetas are non-negative, right? So I don't know, like it just feels to me that maybe in those settings, when you need to truncate, maybe you can just shrink the parameter or something. It might make things easier. I don't know. That seems a possibility.
You mean like project into the simplex, something like that?
Yeah, or like it's literally like just dividing your parameter by constant or something like that.
Yeah.
Because I feel like with the L2 version, it has this problem. Like without that assumption, that there's this issue, right? Like you can, when you shrink your theta parameter, your prediction, you don't know what your prediction, which direction your prediction is going, right? It could be going up or it could be going down. And but if you're in this simplex setting or everything is non-negative, then maybe you know that when you shrink your theta parameter, your function prediction always like goes down, right? Maybe that one-sidedness is helpful. I don't know. That seems one possibility.
Yeah, I think that makes sense, right? Like in simplex, we don't have the negative part of the function, so it seems that this directional thing is.
Right. Also, if you think about like the tabular case, at least on the feature side, is actually a special case of the simplex features. Right. So maybe tabular analysis works because it's actually a special case of simplex. I don't know. It's just a guess. Yeah.
That's a very good direction.
Yeah, I think that's a very good point. Yeah, that makes sense.
Okay, cool. Do we have other questions? Or maybe we should stop the recording now?